Hey, welcome to this last part of the regression lecture. Now, we had in the previous part discussed how we can actually derive our regression parameter better and therewith a function which approximates the samples we have measured or the data we have gathered. If you feel like a lot of this is still unclear and you would rather put hands on something right now, then you can have a look at the accompanying math PDF and maybe go through one of these examples or the exercises in which you are asked to compute by hand one regression function and also the design matrix and all of this. And the solutions will be also there. So if you want to have an example, then maybe have a look first there before you watch this video. Now, this video is about the evaluation of regression tasks. And one of the very important paradigms in regression and its evaluation is the bias-variance trade-off. So assume we want to approximate our true function. Like, this is the goal of regression, right? We want to uncover the grown truth regression function f star, which actually generates our measurements. And we choose, therefore, basis functions for polynomials of degree k. And now in this picture here below, you see the functions we get, which are in red, for different k. So for k equal to 1, the polynomials are actually an affine function. So we get here this line. And you see that it does not really match the samples well, but it's definitely also not able to approximate our function, the true function, well. But we don't know this, right? So we don't know what the true function is. So all we can see are the samples. Okay, but what we can see here is that the samples are not very well approximated, so it seems like the model is underfitting. Then for k equal to 4, we see that it matches the true function actually quite well. And if we look at the samples, then also these are quite well approximated. For k equal to 15, we have here this function which goes very wildly up and down, and it approximates the samples really well, but not the true underlying function. But again, we don't know the true underlying function, so we don't know this. We just see that it's approximating our samples very well. So is this then good? What is the best k? Now, one thing we can of course do is we hold out a test set. So the idea of this is that if the model assumption is correct, then the regression model should be able to predict y for unobserved x. And the idea is then to hold out a test set indicated by the indices I, subset from 1 to n, from the n training data points, and compute the error on the test data. So this corresponds to this picture you probably have seen already. This bar here is supposed to represent all the observations you have. So this is supposed to reflect n observations, but then you hold out here some, and these are in the index set I. And then we use for evaluation here now the MSE. This is the mean squared error, which returns the average squared prediction error. And the MSE is not depending on the size of the test set, which is here the cardinality of our set I, because it creates an average over all these errors we make here, which are summed up here. Where the RSS just sums up all these errors, the MSE computes the average prediction error we make. Okay, so let's do this on our example. Do you see here now that the red dots are the points on which we train our model, and the blue dots are those which are in the test set which are not used during training? And then you see also that for every picture the selection of these dots is the same. And I have made here for these pictures just one simulation of this effect. So I just randomly sampled a test set from my whole data set, which were all the points here, and then I computed the mean squared error. Okay, so for k equal to 1 we got MSE equal to 0.181. For k equal to 4, we got an MSE of 0.015, and for k equal to 15, we got an MSE of 0.002. So the best k is k equal to 15, I mean, if we look at this, then we obviously see that the k equal to 15 is far too large and that this function is overfitting, but somehow, just randomly, the test data points were actually quite close to the function values. Oh, that's a bit shitty, right? So what did just happen? Can that happen often? How can I make my evaluation more reliable? Is the question we're asking here now. And this leads us to this theoretical framework of bias and variance trade-off, which is to minimize the expected prediction error. Okay, so what did just happen? So this calculation of the minimum squared error is in theory a result of the following process. First, I sampled a finite set of my training data dj. Then I learn my model based on my training data. Then I sample a finite test set tj, and then I compute the MSE for this test set. Okay. So if we repeat this sampling process k times, then we obtain k scores for the mean squared error. And with these scores, if we build the average, then this approximates the expected squared prediction error. So this is this big thing which we actually want to minimize. Let's have a look what that means. So we build here the average of all our computed mean squared errors, and then I put in here the definition of the mean squared error. And then this is actually an approximation of the expected value of x, y, and d of our prediction error. So this is what we actually want to minimize. So we want to find a model or a family of basis functions for which we can get a model which minimizes the expected prediction error. And let's have a look now at these constants here. So x and y are actually from the test set here. So this is the expected value over some sample out of the test set, and d is our training data. So this expected prediction error depends on the random variables, which is the particular point I'm looking at in the test set, and the training data I have. Let's make this more concrete. So the expected prediction error has 3 random variables, and x is the random variable of a feature vector in its test set, y is the random variable of the target of x, and d is the random variable of the training data. Now what does that mean that y is, for example, a random variable? Now y depends definitely on x or on the observation. Now we had already said that the process which generates our targets is that I have my true function value and then I add some noise, and this is my target. Now we make this more concrete and denote a probability distribution of epsilon. So f star is the true regression function, and epsilon I is a sample of a random variable epsilon with mean mu and variance sigma square, and epsilon is normal distributed, so Gaussian distributed. I write this here not like this. So that means then that the targets are samples of this random variable y as defined here, and the expected value of y given some observation is the true observation function. This is because the noise has a mean of 0. And the variance of y is equal to sigma squared. So this here, if you wonder where that comes from, this is just a definition of variance. You can look it up if you forgot how that went. But what is interesting here is that we get here again our prediction error, right? Okay, so let's have a look how this variance actually influences our results, or maybe to go through this process of sampling our training data with Gaussian noise. So for example, we consider that our training and test data points are sampled by a process as it's depicted here. So first we sample our feature values, xi here. Let's say I sample here now this value. And then I sample epsilon I from a normal distribution. So I determine here the residual. Then I set yi equal to f star plus epsilon I. So f star is here, but then epsilon I is, for example, minus 0.1. So this is the residual, and then I get this as my data point sample in this one process. And if I increase here my sigma, then of course the residuals are a bit larger. So for example here, if I sample xi to this value 0.9 or something, then here we have f star, and then epsilon I is actually minus this distance here, right? Okay, so the sigma determines how far our samples are actually from our true function value. Now, what is this whole bias variance trade-off about? Well, there are a lot of formulas, as you see, but let's go through this in detail. So x was my feature vector from the training data, and let's just take this out. We can do this by the loss we get by calculating with the expected value. It's not very important that you know how that goes, but what we do here is just that we create here now the expected value over x. We treat it separately, and then we have here x given. So here we consider only one particular feature vector, and then we have the expected value only over y and d, over the training data and the target of our prediction error. So we fix our random variable x to x0, and then we have here that the expected value of over the random variables y and d is equal to sigma squared, which was our noise variance parameter, and then this term and plus this term. And now we see here already that I said that this is bias squared, and below we have the variance. So our expected prediction error for one feature vector is equal to the sum of our noise plus bias squared plus the variance. And what is this bias squared? So here we have the true function value of x0, and we subtract the expected value of my model prediction. So this value is if I compute a lot of models better. So I sample my training data many times, and for every time I sample my training data, I compute a model, and then I build the average. Then this approximates here this term, the expected value of my model prediction for xy. So the bias tells me how far is, on average, my prediction away from the true function value. And the variance is how far is the expected model prediction away from the model prediction I get for one sample of my training data into the square. So this is a definition of the variance between these two measurements here. So that means that we have low expected squared prediction error, so we have good model if we have low variance and low bias, and we need both. Okay, let's have a look at this in a drawing. So here I simulated this effect that I draw my training data set and then I make a model. So every of these red lines is one model, and this value we have seen here, this expected value of my model, is now here set for x equal to 1. So I pick here my x0 equal to 1. I consider only this point here for computing the expected prediction error for the point 1. And then you see here that for k equal to 1, we have here quite a big distance between the true function output, which is here as 0, and the expected model prediction outcome, which is here at -1. So this is here the bias, which is quite high, but the variance is low because the variance is basically measuring how far are these lines here from my expected value, and they are all quite close here, right? Now for k equal to 4, we have low variance at the value 1 because they are also pretty close to each other, and we have a low bias because the expected prediction here at 1 is close to 0, which is the true prediction. And for k equal to 15, we have a high variance, as you might see here for x equal to 1, because here this line, for example, is quite far away from this prediction, and because it is fluctuating so much, the variance is very high. So we get different predictions for one value at every sample for the training data. The model adapts too much to the training data, and then the other points for which we do not have observed variables, there can be very high fluctuations. So this has a high variance and a low bias though, because an average, if you take the average of all these predictions here, yeah, there are a lot of predictions. I did not fake this. This is actually the expected value of my prediction at 1. So on average, everything is fine. But if you have just one, then it's really messy. That is the thing of overfitting. So this model here is overfitting. It has a high variance and low bias. This is the golden balance here, what we want. So it has a low variance and low bias. And this is underfitting. It has a high bias and a low variance. Now, what can we do in practice? This was all theoretically. In practice, we do not have the possibility to just sample our training data all the time independently. We can also work with what we have, which is our data set we got. And the idea is to simulate now this process a bit, and this is by k-fold cross-validation, where we divide the data set into k disjunctive chunks, indicated by the sets I1 until ik. So what you might think here is again like a picture like this. Imagine you have your data set or all the indices. So this bar here is again supposed to represent all your observations. So these are n in total. But now you do k chunks. So this is here for 5-fold cross-validations. We have here 5 chunks. And now we have indices sets for all of these chunks. Of course, we assume here that this should be shuffled, right? Because it's not necessarily that you want to have the indices from 1 to 10, for example, as your first test set, and then 10 to 20 as your second test set, and so on, because there might be dependencies on the samples. So we have here now 5 sets, I1 until I5. And then in one run, we have here, we take, for example, this I1 as our test set and everything else as our training set. So this is here our test set, gets a T. And this is then D for training. And in the second one, you have the second chunk as your test set and everything else is your training set. And then you go on and go on and go on. After all, you get 5 models. So in every one you train one model. You have here beta 1, beta 2, and so on until beta 5. You get 5 models, and then you get also for every model on the test set a mean squared error. And then you can average the mean squared error for all of your models, beta j. And then you get here this cross-validation mean squared error, which is the average of all the mean squared errors that you got. Sorry, I have a mistake here. This should be k. We have k-fold cross-validation, so here we have k. And again, so this here is just a definition of the mean squared error, as we had it. Okay, question. Is the cross-validation mean squared error in general a good approximation of the expected prediction error? We can discuss this in the lecture. And now let's have a look at an example. So we make here a 3-fold cross-validation for training a polynomial with k equal to 15. So we divide here our data set, which are all the dots which are here plotted, into 3 chunks. And then we get 3 test sets, a different one for every one. And we train our model on the corresponding training set. And then we get for every model also a different test mean squared error. So here we have this first example we had where the mean squared error is pretty low. So the separation into test and training data is actually too beneficial for this kind of function. And then we see here that for the second run, we get a much higher mean squared error. So all of a sudden it's 195, and this can get really, really high. For example, here it's most obvious for 533, because you see here that here, for example, it goes down a lot, and the actual data points lie here. So as a cross-validation mean squared error, you can get the average of all these mean squared errors, and this is 242, so it's really high, and this tells you that this is not a good model. But from the mean squared error, you cannot see if it has high bias or high variance, and what it is that it doesn't make a good model. We only know that it's not really good. Okay, so this concludes our lecture for now. The takeaway here is that the bias variance trade-off is a theoretic measure of over and underfit in a regression model, and I hope you have understood in which way the theoretic framework is interesting on the one hand, but also that it is not possible to compute the bias and the variance so easily. But at least we know that what are the characteristics of a model to be actually good and what has to be fulfilled. And then there are these workarounds of getting some practical information about the fitness of a model, which is then the cross-validation. Yeah, I'm curious about what you think about this. Do you have some remarks, questions, ideas how to improve this? I want to hear it in the upcoming lecture. Until then, have a good day.